We now have Merve and Thomas from Ericsson. Let me just get your talk up. It's an anonymous title. It's a big mystery. Ta-da! Right, I now know what you're talking about. Scaling CHERI use after pre-protections to millions of allocations. So they've both been looking at scaling temporal safety for industrial workloads and using colored capabilities. Thank you very much.
Yeah, thank you very much, Simon. We want to talk a little bit about this joint work that we've done together with the University of Waterloo in Canada, the KTH Royal Institute of Technology in Sweden, and KU Leuven through an internship done at Ericsson, and last but not least, also University of Cambridge. And we've been sort of really, I think, grateful for this collaboration. So apart from John, who spent engaged with us directly on the prototypes, we are also happy to have been worked with Peter and Alfredo on who helped on us reproducing some of the old benchmarks from the earlier temporal safety papers. So going back to this kind of like earlier research can be sometimes troubling, so we are grateful for that support. Yesterday and earlier today, there were several talks in which temporal safety was kind of highlighted as a sort of a hot topic or an area of interest. And this is sort of our attempt to look at things that would allow us to evolve the CHERI architecture towards more performant temporal safety without changing the underlying mechanisms currently standardized, but perhaps by revisiting some of the design choices that have been done over the years. And I will sort of give a brief introduction to some of these motivations and what kind of design choices we want to revisit. And Merve will then talk about sort of the actual temporal safety enforcement. But let's talk about this sort of central design choice in CHERI, which is about avoiding indirection, right? So this is something that's very sort of explicitly a part of CHERI. It's even so like mentioned several times in the original Cambridge specifications. So we kind of like know why CHERI has made these choices. And this sort of means that CHERI by design avoids table-based lookups capabilities. So if you look at some of the historical capability architectures, you see designs where you have capabilities that essentially are just numbers, right? And that number points into some table in memory, and that table has the actual attributes of the capability and the address into memory. Or then you can have this kind of indirection based on pointer operations that essentially gives you the same kind of mechanism, but it costs you this additional lookup through this intermediate. But there's some benefits to some of these classical architectures, right? So one interesting property here is that we have this sort of central place where we can either alter or revoke capabilities. And this is particularly interesting in use cases where we want to revoke capabilities in bulk, right? So if we have this kind of construction, we can essentially very efficiently revoke sets of capabilities by revoking this intermediate entity. As we heard earlier today, you know, the trade-offs in CHERI in avoiding this sort of indirection is this revocation sweep, right? So in CHERI, if we want to revoke a capability, we have to know its and its validity tags location in memory. And that means that if we want to invalidate sets of capabilities, as in typical in temporal safety enforcement, we actually have to sweep through the memory to find those instances of capabilities in order to revoke them. And the strategies we have today to speed this up involves this limiting the search to specific pages, as is done by the Cornucopia Reloaded paper and sort of the current RISC-V standard drafts. And by parallelizing sweeps, right? So Alfredo talked earlier about how this is sort of done today in CHERI BSD by a kernel thread, and this sort of buys you some performance But in use cases where you are care about sort of the dimensioning on the systems against sort of worst case performance scenarios, this is still troublesome, because even if you are able to parallelize these kind of sweeps, it still consumes overall CPU time from the system as well as memory bandwidth. So this is a kind of like a trade-off which does not fit all types of systems. It doesn't fit especially like systems with real-time guarantees or like certain types of high-performance systems. And while there are some very good work in accelerating temporal safety for embedded systems, and that is getting fairly mature, we don't really have good ways of handling this for application processors. So what we sort of try to do is sort of like rethinking this notion of indirection, one of the things that is maybe sort of like an obvious question that CHERI design seems to be doing quite well without indirection, right? So do we actually even need this? But then if you look at these temporal safety schemes we have today, they actually all have some indirect way of tracking this information about which capabilities we want to invalidate. So in Cornucopia and Cornucopia Reloaded, we have the shadow bitmap, which essentially tracks memory, allows us to go back into those capabilities that we want to invalidate. And in Chariot, this is sort of even more explicit, right? So we have the revocation bitmap and load filter that sort of handles this same kind of functionality. But we still have this problem, right, that if you want to build like this indirection on every capability access, that is very costly. So can we apply indirection selectively only to certain capabilities where we actually benefit from this property and minimize the impact on the overall system and the microarchitecture? So this is sort of like the motivation behind this work around colored capabilities. And there is sort of quite a bit of sort of work that went into the hardware implementation that we are not able to cover in this talk. So I will just give you an overall idea of what colored capabilities are, and then we will look at how do you actually build temporal safety using this. So colored capabilities are a way to introduce a very limited form of indirection into the CHERI architecture without changing the sort of the underlying principles behind CHERI. And what we use colored capabilities for is that we track something we call allocation provenance. And that means whether a capability actually corresponds to a valid allocation at any given time. So this is now important to note that we, in like the CHERI specifications, they also talk about provenance, but typically they talk about the capabilities on provenance, right? So how did we get this capability? Is it coming from a valid source? When we talk about allocation provenance, we are talking about, does this capability point to a valid allocation, and is that allocation still valid at the point when we are dereferencing a capability? We do not track which allocation this capability points to, right? So you can maybe infer that through the address, but the mechanism we added is essentially adding a single bit of information that tells you whether the allocation from which this capability originated from is still valid. And all capabilities that share the same allocation provenance, so they originate from the same malloc allocation, they also share something we call a provenance ID, which in practice is the object type, is stored in the object type fields. And this is where we sort of like we sort of like refer to the object type field when it's a provenance ID as the color of the capability. But note we call it color capabilities because we are coloring only the capabilities as opposed to sort of memory coloring schemes where you associate the color both with a pointer as well as a memory location. So here the color is only in the object type. And that object type is then used to track a 1-bit entry in something we call the provenance validity table, which is managed by hardware, so here abbreviated as PVT. So the color of the capability as an index into the PVT, and this gives you the provenance validity bit, which tells you whether this capability is actually valid at any given time. Then capability with a provenance ID, but for which the provenance bit indicates this capability is no longer valid, are temporarily retracted, right? So remember, we cannot revoke them without actually doing the capability sweep, so we essentially just disable them. And you can think of this as essentially a type of sealing which is sort of externalized based on the status of this provenance validity bit. We sort of call this retracting, not to sort of confuse this notion with a sealing. But in this architecture, you can still do traditional sealing by essentially reserving a specific area of the object type space to sort of the current way CHERI deals with sealing, and then the rest of the object colors or the object types as colors, as provenance IDs that we use as indexes. Yeah, we also have I'll mention it here, that we have a slightly modified capability format which gives us, I think, 3 additional bits of for the object ID. So we have, I think, 21-bit object ID. So in practice we have a bit over 2 million different colors. All right, and then I will hand over to.
Okay. Does this work or yeah? Okay. Normally, I believe that color capability is some concept, and we think that you can use it on different concepts. And one of the things that is we use it for temporal safety. I know that people already discussed, but I want to highlight again what is the difference between what is the user after free and what is use after reallocation. Assume that you have udo as a malloc, and after that you free it. And after this period, if you access, we call temporal safety. If you access directly after the free, we call user after free violations. But the problem started with that if the P memory actually is allocated to another pointer. If you access after that point, we call user after reallocation bugs. And actually, when attack happens when user after free reallocations bugs happens. But both of them is called as a user after free bugs. Some of the approaches apply user after free. Some of them is say that, yeah, okay, I want to do some solution for user after free reallocations. They already give us some quick introduction to cornucopia. Alvarado did it, but I want to highlight something here also. When you do a free, we put the memory in quarantine, and we say that we mark it on the shadow bitmap, saying that this region is freed. And we want to, they want to make sure that this memory will never reallocate it until the revocation phase is handled. But when I checked this scheme, I found a couple of things. Firstly, it handles the gap that I mentioned. It only addressed the user after free reallocation bugs. The second thing is that there's just some problem here that if you want, you can put a lot of things on the quarantine memory. What will happen that your memory overhead will go up. If you want, you don't need to use quarantine buffer. Whenever you do free, you can do revocation. So what will happen that you will pay a lot of CPU costs, a lot of performance costs, right? So as a result, use of quarantine buffer increases memory usage. Revocation frequency scales conversely with the memory overhead, right? This is an early approach that is proposed in the CHERI ISA, and I saw also some couple of GitHub issue that can be combined CHERI with the memory tagging, the close this gap, mitigation gap. How it works that when you have a capability, on the allocation side, you color both the color and the memory. When you do free, you recolor the memory that any dangling pointer cannot access. But the problem is with that, if you use MTE, you will have 16 different ID, right? And when the color is exhausted, you will fall back to the cornucopia. You will still, again, the quarantine the freed memory, and you will have the same problem. Even though if you address this gap, assume that you are able to only shift, if you have a 4-bit tagging, you can only shift for 16, right? That's why I can say that even though there is no technical implementation, I cannot compare with my solutions, but I can say that it has the same disadvantages as cornucopia. So what is my goal? I want to close this gap, and I don't want to quarantine any buffer. I want to immediately use the memory, and also I want to reduce the frequency of revocation sweep, how much I can postpone. This is my goal. So to handle, as a solution, we propose color capability. How it works that on allocations, I assign some unique provenance ID, and on free time, I'd say that this allocation is already freed. And the nicest thing is for this approach that I don't take color or memory. I have a different validity table we call provenance validity table, and hardware always supposed to check that whenever load and store happens, it needs to go and check that this PVT is valid or not. So I can detect the user after free bugs. With this approach, we address this gap, and as you see that I don't need to use any quarantine buffer. I can immediately use the memory, and also revocation frequency scales with the number of supported colors. What I mean that, as Thomas has mentioned, that we use totally 21-bit O type, so I have 2 million color, right? Even though if I don't need to quarantine the memory, I need to quarantine the color. I cannot give the same color before revocation sweep happens. So we implement this one on both QEMU and CHERI Turbo Core. We have a lot of different details, but now I am seeing that I have only 3 minutes. And also, I just want to mention that this is really a colorful figure and it hurts your eyes. It hurts me also when you are implementing this stuff, or it hurts all of us. I can just say it was not easy, right? But especially the nicest thing is this approach that we implement this PVT buffer caching inside the hardware. So we cache always that whenever who accesses, we store in the hardware that who accesses, and it scale up a lot. This one is implemented by the John, I should say. It improves our performance a lot. So we integrate also on the color capability on the CHERI BSD, memory allocator, and we have a revocation mechanisms slightly different than the current implementations. But maybe you are more interested in the evaluation part. I evaluated on 3-phase. Can PICASSO reliably detect the user after free conditions, and what is the performance and memory overhead enforcing temporal safety with PICASSO? And the most importantly, that how much I can postpone the revocation sweeps. We evaluate using Juliet test suite. We can detect everything, including user after free, double free. If you compare with cornucopia, of course, in default configurations, it will not able to detect the user after free, because the reason is that you don't enter the revocation. When you enter the revocation, you can detect. However, if you enable that part, it will be so costly, right? So as a result, PICASSO achieves deterministic detections. The second thing is that what is the benchmark result? We have 5 percentages in geometric mean spec performance overhead. Cornucopia has 11% in single core and 8% in dual core. For memory overhead, most of the time we don't have any overhead on PICASSO, as I explained that we don't quarantine any memory. Considering time, I will just show real workload. This is the SQLite. For Picasso, I have 8% overhead. Cornucopia has 12% overhead. Especially for memory overhead, I want to highlight that again, I don't have any memory overhead. This Cornucopia has almost 100% memory overhead across the whole benchmark. The second benchmark is that we run PG bench. This is very interesting. Why it is interesting? Because if you run the cornucopia, every 20 transactions, you are entering a revocation phase. So when you enter the revocation, you see a tail latency. So it is so clear here that you see the pattern. Whenever every 20 transactions, you see some peak latency. However, Picasso, sorry. However, on Picasso, we can run so long term. This is the things that I want to show you, especially most of the time Picasso never entered the revocations, because if you need to enter the revocation totally, you need to do 2 million allocations, right? And I explained that for PG bench, every 20 transactions that cornucopia enter the revocations, but for color capability, we enter only 66,000 transactions. It is really a lot. Yeah, and also I run so long term with Picasso to enter the revocations. However, we never increased any latency, including the P999. So I think I should be stopping now because I already overload a lot. Sorry for the rush. Yeah. Okay.
You want to go through the conclusion?
Yeah, that's okay. I think everybody's doing that.
Well, thank you very much. Wonderful work. It's always nice to see better security and better performance.
Yeah.
So well done. Are there any questions?
Now I'm escaping. That was it.
So you said no memory overhead, but there is memory overhead because you have to have your bit table of revocations. So if you go back a few slides, or maybe not. But anyway, you said there was no memory overhead for Picasso, but there is a memory overhead because you have this bit table lookup. Right?
Yeah, so that's true. So there is the bit table. You can say that's a memory overhead. That's a fixed size. That depends on kind of the size of the color space.
It's
Just say which shovel bit. Yeah. Okay. Yeah. Also, if you are interested, also we have some small software stuff that is normally I need to have some way of to manage the 2 million allocation, 2 million object ID, right? Who is revoked? Who is not revoked? Who can give? And this is done by some FreeBSD unit allocator, and at the end I understood that one is also has a memory overhead on Picasso. Yeah.
And the other thing obviously is now you can't use O-type for O-type.
Sorry?
Now you can't use O-type to be a type, which is what its intended purpose is.
No, you can. So we have a mechanism that allows you to select which part of the O-type field you use as an ID, as a provenance ID, and if you have systems that need O-type, but typically we found that they don't need that many O-types because even the compartmentalization doesn't use O-types anymore. But for like if you have like a small number of O-types you need to reserve, you can configure that in the hardware. It's like a register that you. But obviously the more of the O-type space you want to reserve, the less is available for the coloring. So this is a kind of a characteristic that you can tweak. Yeah.
Okay.
Yeah, but also I want to say that, for example, this is a call for action. If you give me more O-type, I will never maybe enter revocation. Right? Standardization team is here. Give me more O-type. Yeah.
You talk to Rob. Just behind.
Yes, thank you. I guess you've described having to access memory additional times when you want to check to see if something's revoked, and that you therefore, and presumably you were therefore interested in having some kind of cache on it, and you mentioned John worked out. Could you tell us about the coherency properties of that cache and whether you require invalidation explicitly?
Yeah, so what we currently do is that we basically, whenever you are updating the bitmap, we are doing fences. So that obviously has like both a performance impact and like a coherence impact. So we are currently looking into sort of adapting this for multi-core architecture. So what we are sort of are experimenting now is that instead of like doing flushes, we basically want to have sort of selective flushes that update the buffer directly, and I think we can solve part of the coherency problem by sort of having this selective update. So that's something we are looking into now. But
I guess
currently,
the natural comparison might be a TLB. Is it
Yes.
reasonable to think about it as being like a TLB in terms of its cache properties?
it is reasonable to think about it as a TLB, I think. Yes.
Yeah. So I guess in risk you would need explicit per core invalidation with
Yeah.
IPIs between the cores or
Yeah,
something.
yeah. So this is still sort of like fairly early work, right? So,
Yeah,
so
yeah. I
we
mean,
are
some
like- yeah.
in the ARM microarchitectures and architectures, they're able to do remote TLB invalidation without IPIs, but I'm not aware that people are doing that with RISC-V currently.
Yeah, yeah, yeah. But we will see how far we can go with
Yeah.
this, right? So, but this is sort of like an initial, and then there's also like you have workloads that need more than 2 million allocations. So we are also looking into.
Yeah, Omnet PP is decidedly distressing that way.
Yeah.
Yeah. And is it reasonable to think of the color really as being an object ID? Or like a memory allocation ID because it uniquely identifies the allocation that's applied?
Yeah, you can reasonably call that as well, right? But I think sort of the intuition with the color is like coming from the work on the memory version, right? Where you
Yeah.
yeah.
Shall I pass it back to safe?
Great. Well, thank you very much, guys.
Thank you very much.
Super.